Thanks for coming, everyone. It's my great pleasure to introduce to you today Ruth Shatkay, who's going to be presenting her master's exit seminar. Her project is titled Relationships Between Forest Patch Characteristics and Near Ground Solar Radiation in Baltimore, Maryland. Ruth was an undergraduate at the University of Maryland, and she did some really great stuff as an undergraduate. She was part of a gemstone honors project that looked at the solar decathlon house. She was also a Banneker Key Scholar, very prestigious scholarship. She earned her Bachelor of Science in Architecture with a minor in hydrology, which really made her an excellent fit for the kind of work that we are doing in our lab at the interface between built environments and ecological processes. And that's the kind of niche that Ruth has fit herself into. Her work, as you'll see, is part of an ongoing collaboration that our lab is doing with some researchers in Forest Service at UMBC and nonprofit up in Baltimore to characterize the ecology of forest patches up there. So Ruth has done an excellent job establishing a field project in the context of this broader set of questions that we're working with, navigating the pandemic as she's done it, learning a whole new system for capturing data and processing. She's done a really fantastic job with it all. So without further ado, I will let Ruth take the stage and present the work that she's been doing for us.
Great, thank you for that introduction. And here we go. Great. So thank you again, and thank you all for being here today for this talk about my master's work, where I looked at relationships between urban forest patch characteristics and near ground solar radiation in Baltimore, Maryland. And just a warning, my internet is a little spotty today, so hopefully it all works throughout. But if something does happen, I'll try to be back soon. So to preview, I'll be going through some background on urban forest patches and solar radiation and my objectives, which will make up the first chapter of my thesis. And then I'll talk about my study methodology, our results, and some of the implications of this work. So what are urban forest patches? So following a definition by Miriam Avens, we defined urban forest patches as areas of contiguous canopy that are 10,000 square feet or larger. And in Baltimore specifically, they compose about a third of the city's overall tree canopy. So here you can see this is an aerial view from north central Baltimore, and you can see all of these kind of large swaths of forest scattered throughout the city. Forest patches are important because they perform a variety of ecological functions and provide a range of ecosystem services like temperature moderation and stormwater management. And these services can be influenced by the density of the forest canopy, as well as driven by solar radiation. Because we're in Baltimore and in the Chesapeake Bay watershed, stormwater management is obviously really important here. So I'll look at some of those implications in a little more detail. So here you can see that the tree canopy impacts interceptions. So the denser the tree canopy is, the more stormwater it's able to intercept, so the less that kind of goes down as throughfall and becomes stormwater runoff. Solar radiation is also important because it drives tree transpiration, which cools surrounding environments. So in hot urban areas like Baltimore, this can be like an essential function. And you can also see here that in these gaps in the canopy, solar radiation will reach the forest floor and drive soil evaporation. So this can negatively impact plant and root growth. So for my thesis, I looked at both of these variables, canopy density and solar radiation. But today I'll only be talking about the solar radiation component of this work. So what is solar radiation? It's the electromagnetic energy emitted by the sun. So you can see here that includes UV radiation, visible light, and infrared radiation. It can be direct, which means it's transmitted unimpeded from the sun through the atmosphere. So that's kind of like the glare of the sun that you feel on a cloudless day, a clear day. Or it can be diffused, which means it's scattered by the atmosphere. And that's what would be kind of dominating on a day like today when it's cloudy and overcast. Um, and because of the way the sun moves across the sky, solar radiation inputs to surfaces are strongly influenced by topography. So here you can see the sun moves south across the sky. So south-facing slopes would receive more radiation than north-facing ones. Um, Here you can see that solar radiation is also influenced by slopes. So slopes that are more perpendicular to the sun's angle in the sky would receive more radiation. So in the summer, when the sun is pretty high in the sky, flatter slopes would tend to receive more radiation than steeper ones. And because we're looking specifically at forest patches, we'll note that near-ground solar radiation varies with the tree canopy, so leaves will absorb and reflect a good portion of the incoming radiation, but some radiation will also be transmitted through the leaves as well as through gaps in the forest canopy. So linking what we've talked about together, forest patch attributes like edge environments, topography, the presence of invasive species, patch histories, and management regimes influence the structure of the forest canopy. This in turn will impact the amount of radiation that reaches below the canopy, and below canopy radiation drives plant growth, photosynthesis, evapotranspiration, seedling establishment, and species composition, as well as influences some soil characteristics like soil moisture, soil temperature, and soil evaporation. And these characteristics affect root growth, water and nutrient uptake, nutrient cycling, decomposition, and soil biological activity, all of which link to the provision of ecosystem services. So for this project, I was interested in looking at the top of this chain at how patch attributes influence below canopy solar radiation. And that brings us to our research objectives. So first, we wanted to assess the influence of patch origin on near-ground solar radiation. And by patch origin, what we mean is that patches can be what we call remnant, which means that prior to urbanization up until today, they've existed in the landscape as a forest patch. They can also be what's called regenerated, which means that at some point they were a forest patch and then they were cleared for some other kind of land use or development like agriculture or residential structures. And then they were abandoned and left to their own devices. And today we see a forest patch, but at some point in the past they weren't. And we classified patches as either remnant or regenerated based on the analysis of aerial photographs from 1927. So if a site that we were interested in was a forest in 1927, we called it a remnant patch. And if it was something else in 1927, so most often that was agricultural land use, we classified it as regenerated. And we were interested in seeing if there was a difference in solar radiation inputs between these two patch types. We also wanted to quantify the solar radiation and its variation from the edge to the interior of urban forest patches. So as we move from the kind of center of the patch out towards the edge, do we see changes in solar radiation inputs? And finally, we wanted to assess the influence of topography. So we looked at slope and aspect and the presence of vines on near-ground solar radiation. So how did we do this? Here you can see our first step was site selection. So for the past few years, as Mitch mentioned, approximately 40 forest patches marked by these little dots throughout the city of Baltimore have been studied and characterized by the Baltimore Ecosystem Long-Term Ecological Research Project in collaboration with a couple other groups like Baltimore Green Space, UMBC, and the U.S. Forest Service. And so all of these groups have looked at a number of forest characteristics in all of these patches as part of this like long-term work to study urban forests. So to select the patches for our study, we started with these 40 patches and then selected only ones that were located in the Piedmont Plateau physiographic province, were larger than 3 hectares, had at least 20 sampling points where these groups had been looking at characteristics, were at least 75 meters wide, and were not fragmented by roads or other infrastructure. And once we used these criteria to select our patches, we were left with 6 forest patches to study. So those are these 6 sites marked by the larger circles and letters. So here you can see what those sites look like. So we have Carroll, Fendel, Forest Glen, Sinai, Heron, and Village Square, and they range in size from 4.4 hectares to 13.8 hectares. So now that we have the sites, we needed to determine below canopy solar radiation at them, and the way we did this was using hemispherical photography, which is a technique for characterizing plant canopies using photographs taken through an extreme wide-angle lens. So here, this is an example of a hemispherical photograph. So we have the camera set up below the canopy looking up, and then we can take a photograph that captures this full hemisphere of a canopy and sky. And from a photograph like this, we can model solar radiation to efficiently assess the below canopy solar radiation conditions, as well as a number of other forest characteristics. And to take these photographs, we based our sampling protocol off of a system that was previously established by our collaborators at UMBC. So here you can see this is one of our patches, and all of these white dots denote these sampling sites that they had established, and they measured a number of different characteristics at each of these sites. So some of the ones that they measured that we were looking at were aspect, so the direction that the slope faces, and the slope angle, so how steep or flat it was at each site. And both of these values they determined from a digital elevation model. We are also interested in looking at the distance of each sampling site from the patch edge. So that would be like the closest, the distance from the closest edge. So here you can see some of those are marked with these red lines. And these distances were determined from doing a spatial analysis using ArcGIS. And the last characteristic that they looked at that we were also interested in was vine invasion, so the presence of species like English ivy at each site. And that was determined from some field sampling, and I'll get into how they calculated vine invasion a little bit later on in this presentation. So going back to this established sampling grid where they have taken a number of measurements, we took our photographs at these alternating grid intersections along the same sampling grid. So here you can see like at every other sampling site, we took a photograph. And using this method, we ended up with 10 samples in Carroll, 27 in Fendel and Forest Glen, 28 in Heron, 18 in Sinai, and 17 in Village Square for a total of 127 samples or photographs. And this is an image of how we took the photographs. So at each sampling site, we set up the camera on a tripod at 4.5 feet above the ground with the lens pointing up. We also put a north indicator in the ground in the direction of north. So that's like a 5-foot or so tall pole that would be used to tell us what direction north was in our final image. And here you can see how that looks. So here's a photo from our site. Here's our camera with the lens pointing up. Here's our north indicator. And here's the image from that site. So you can see we've got this north indicator at the top of the image. This is telling us that this is where north is. And when we collected these photographs, the most important thing was to get this high contrast image where you could clearly see the difference between the tree and the sky. So to do this, we took the photographs at around dusk throughout the summer of 2020. And we went at around sunset because that's when there was no glare from the sun. And so to get this high contrast image, we first took one photograph, and then we used this function on the camera called highlight alert that basically shows all of the areas of the photo that are overexposed. So here you can see an example of that with these black splotches that are flashing, indicating the parts of our image that are overexposed or too bright. So to kind of resolve this, we adjusted the exposure of the image incrementally until we got to this image that had no overexposed areas, and you could clearly see the difference between the tree and the sky. So we would select this last image to analyze for solar radiation. So for the photograph analysis, we used HemiView, which is a Canopy image analysis software. And the first step of doing this was to binarize the image by selecting a threshold value. So that's the value under which all of the pixels in that image would appear as white and over which all of the pixels would appear as black. So here you can see this is our original image that we're choosing to analyze. And here would be the binary image. So the trees are these black solids through which no radiation can pass. And these sky gaps are voids where radiation can be transmitted to the ground. And from this binary image, we were able to calculate the amount of radiation transmitted below the canopy. And the metric that we used to do this is a proportion called global site factor, or GSF. And this is the amount of diffuse and direct radiation transmitted below the canopy. And we were just looking at the summer months, so June, July, and August, over the amount of diffuse and direct radiation above the canopy for that same time period. So the value would range from 0 to 1, with 0 being no radiation transmitted through the canopy, so that'd be like a very dense canopy, and 1 being a completely open area where all the radiation is transmitted to the ground. And to kind of give you a sense of what that looks like, here you can see this would be a site factor of 0, where we have like no light passing through the canopy. Here would be a site factor of 0.11, so we have a little bit of a more open canopy, and that means that about 10% of the total radiation is transmitted through to the forest floor. Here, still a little bit more open with a site factor of 0.21, so that means that about 20% of our total radiation is transmitted to the forest floor. Here's a more open canopy with a site factor of 0.45. Here's a very, very open canopy, so about 75% of the total radiation at that site is transmitted through the canopy to the forest floor. And finally, here would be a completely open site with a site factor of 1. And briefly getting into how these site factor values are calculated, we calculate diffuse radiation using the sky map, which basically divides the image into these different sky sectors, and then you can measure the transmission of diffuse radiation over space across the whole image. So in this case, the total diffuse radiation that's transmitted below the canopy during the time period we looked at was 160 or so megajoules per square meter, and that would be relative to the 1420 megajoules per square meter above the canopy. So again, we're looking at variation in diffuse radiation over space. For direct radiation, because it's transmitted directly from the sun, it's calculated using this sun map, which shows the path of the sun in the sky over time. So first I'll note that east and west are flipped from what we would typically expect because the image is looking up rather than down. And so this path that's highest in the sky would be our June 21st, our summer solstice, and this path closest to the horizon would be our winter solstice, so December 21st. And these vertical lines are the time frames throughout the day. So we have sunrise in the east, sunset in the west. And because we're looking only at our summer months, we integrated this sun path over time from June through August. So that's shown by this kind of hatched pattern. And so we're looking just at direct radiation in this section. And for this site, what we found was that 240 megajoules per square meter were transmitted below the canopy relative to the 1660 above the canopy during that time frame. And so for our global site factor value, again, we're looking at the total radiation, so both direct and diffuse. So when we sum up the amount below the canopy over the amount above the canopy, what we find is at this site, our site factor value is 0.13. So that means that, again, 13% or so of the total radiation at that site is transmitted below the canopy, and then about 87% would be captured or reflected by the tree canopy. And we used HemiView, the canopy analysis software, to calculate all of these values at all of the sites where we took photographs. So that would give us our full data set of these site factor values. And that brings us to our results. So our first question was, how does patch origin influence solar radiation? And here you can see the site factor distributions or the solar radiation distributions for the remnant sites, which again are sites that have existed as a forest in the landscape since prior to urbanization. And here's our distributions for our regenerated sites, which were cleared and then reforested. And from a Mann-Whitney U-test, which is a non-parametric analog to a t-test, so we're comparing the medians here. What we found was that there was no statistically significant difference in the solar radiation inputs between these two sites, or between these two patch types. And ecologically, what this means is that it's taken less than 100 years for these regenerated sites to develop a canopy cover that's comparable to these remnant sites. So that's a pretty fast rate of succession and indicates that urban reforestation projects could yield promising results in a pretty short time frame. We next compared solar radiation between the 6 patches that we sampled. So here you can see these are our 6 different patches, and here are our solar radiation distributions. And from a Kruskal-Wallis test, which is a non-parametric analog to single factor ANOVA, so again, we're comparing medians here, what we found was that there's a significant difference between in the distribution of site factor between Village Square and the other 5 sites, as well as Forest Glen and the other 5 sites. And based on these findings, we decided that for the next phase of our analysis, we would split the patches into 4 different categories. So first, we would look at all of our sites together. So we'll look at all values across the full data set. Then we would look at Carroll, Fendel, Heron, and Sinai as a group because there was no statistically significant difference in the site factor distributions amongst these 4 patches. And we would also look at Forest Glen alone and Village Square alone. So here we've got our 4 different patch categories. And that will bring us to our third question, where we asked, how do topographic variables and forest characteristics influence solar radiation? So again, here are our 4 patch groupings. So we have all of our sites, just Carroll, Fendel, Heron, and Sinai, Forest Glen, and Village Square. And the 4 variables that we were interested in looking at were aspect, slope, distance to patch edge, and vine invasion. And from a multiple regression analysis, what we found was that there was no significant relationship between solar radiation and aspect at any of our sites. There was no significant relationship between solar radiation and slope at any of our sites. Across all sites and in Village Square, there was a significant relationship between solar radiation and the distance to the patch edge. And across all sites, in Forest Glen and in Village Square, there was the significant relationship between solar radiation and vine invasion. So going into a little more detail about how aspect and slope influence solar radiation, here you can see a plot of our site factor or solar radiation inputs against aspect, so that's measured in degrees from north. And here on this plot, Carroll, Fendel, Heron, and Sinai are represented by these open circles. Forest Glen are these closed circles, and Village Square is represented by these triangles. And as you can see, there's obviously no clear relationship between site factor, solar radiation, and aspect. What we had expected was that solar radiation inputs would be higher on these south-facing slopes, kind of increasing until around 180 degrees or due south, and then decreasing again. But that's not what we saw at all. So we determined that aspect does not affect below canopy radiation in these forest patches. We next looked at how slope interacts with solar radiation. So we divided our slope into 2 categories. Here are south-facing slopes, and here are north-facing ones. And as with aspect, we found that there was, again, no significant relationship between solar radiation inputs and slope. And we were a little bit surprised by these results. We had expected to see a decrease in solar radiation as slope increased. But the results that we found are pretty much in line with findings from a previous study done by Zhao et al., where they looked at the effects of slope and on solar radiation in a range of different canopy covers. So what they did was they took one single hemispherical photograph and then modeled different slopes and calculated solar radiation at different slopes using that same canopy image. And in the summer under high canopy cover, what they found was that both on north-facing slopes shown by this black line and these open circles are south-facing slopes. So on both of these, there's a very, very minimal effect of slope on solar radiation inputs. So that would indicate that these variations that we see are not driven by slope or other topographic variables, but rather are really a function of canopy cover. So we shifted our approach instead to look at forest patch characteristics that might influence canopy cover. And one factor that we were interested in was the distance of each sampling site from the edge of the forest patch. So we thought that might affect canopy cover throughout the patches. So that brings us to our next question, which is how does the distance from the patch edge influence solar radiation? So here you can see this plot of global site factor, so our solar radiation metric, against the distance to the patch edge. And here you could see this image at a higher radiation site and a lower radiation one. And across all sites, what we found was that very little of the variation that we see is explained by this relationship. But there still is this small but significant trend that as distance from the patch edge increases, solar radiation inputs decrease. So more interior sites will receive less radiation than ones close to the patch edge. And looking at each individual category, We didn't see this relationship in Carroll, Fendel, Heron, and Sinai, nor did we see it in Forest Glen. But looking just at these triangles at Village Square, we found this quite strong relationship exists between solar radiation and distance from patch edge, with this edge site having these edge sites having much higher radiation inputs than these more interior sites. So overall, what we found was we do see that as the distance from the patch edge increases, solar radiation decreases. And finally, the last variable that we looked at in our regression model was at how vine invasion influences solar radiation. So first, getting into this vine invasion component, our collaborators at UMBC created this indexing system to assess vine invasion with. So what they did was they ranked the presence of vines on different trees around each sampling site on a scale from 0 to 5. So 0 would be a tree with no vines. 1 would be a tree with vines growing on the bottom of the trunk. 2 would be when vines are growing on the trunk but still below the canopy. 3, when vines are growing into the canopy. 4, when vines are covering the majority of the canopy, and 5 would be when vines are covering the entire canopy. So for every tree around each sampling site, they indexed it, and then they averaged all of those values for all of the trees around the sampling site. So we'd have one vine invasion value per sampling location. And using this index, we found that across all sites, there's this small but significant relationship that as vine invasion increases, solar radiation inputs increase. So here you can see this is a less invaded site with lower radiation, and here's a more invaded site with a slightly higher radiation inputs. And as before, we didn't see this relationship in Carroll, Fendel, Heron, and Sinai, but looking just at Forest Glen, we saw it more strongly. So again, here we've got our low invasion, low radiation site and our high invasion, high radiation site. And we also saw it in Village Square, this low invasion, low radiation, high invasion, high radiation trend. And of course, in this site, we have very few data points, and the distribution's a little strange, so the test here isn't very strong, but overall we did find that this relationship exists with vine invasion increasing as solar radiation increases. So to recap, we found that there are some significant relationships between these urban forest patch characteristics and solar radiation. However, we also noticed that these relationships didn't hold true across all of the patches that we looked at. And in many cases, they only accounted for a very small fraction of the variation that we saw. So looking at this, I was drawn back to our earlier analysis here, where we were comparing our solar radiation inputs among these 6 patches. And none of these characteristics that we looked at really seem to explain why we see these differences between the sites. So to explore what factors might be causing this between patch variability, we decided to look at how patch shape and complexity might impact solar radiation, so how these different shapes might affect these inputs. And to do this, we use this metric called compactness, which is just a measure of how circular or elongated a patch is. So a circular patch is like the maximum compactness, and then like a line would be the least compact. And so when we plotted our median solar radiation values in each patch against that patch's compactness index, what we found was this quite a strong trend that as patches became more compact, their solar radiation input was lower. So here you can see in Village Square, our least compact, most elongated patch, we have the highest median solar radiation, whereas in Forest Glen, our most compact, most circular patch, we had the lowest median solar radiation inputs. So what does all of this mean, and where should we go from here? So again, we found that near ground solar radiation is higher, closer to patch edges, at more invaded sites, and in less compact, more elongated patches. And ecologically, what this means is that at these sites, less radiation is driving these above canopy processes, so we'd have lower rates of transpiration. We'd also have more inputs to the ground level, so soil evaporation would increase, and that would cause a decline in soil water availability, which can impede plant and root growth. So to mitigate these issues, we suggest implementing planning and management strategies that will minimize the presence of invasive vines, patch edges, and elongated patches. And we also suggest prioritizing the conservation of more compact patches, like so patches that have denser canopies and let in less radiation through the canopy. We also came away from this work with a few more questions. So here you can see again that we saw this clear trend of solar radiation being higher at these more elongated sites. But of course, with only 6 patches, so we really only had one median value per patch, our test isn't very strong, like we only have 6 values to look at. So we're wondering if we sampled more patches, would this trend continue to hold? And again, we need more data points to draw stronger connections, but if this relationship really does exist, this information would be valuable for planning more effective reforestation projects in urban areas. We also found that solar radiation was higher at closer to the patch edges, but there were a couple factors that we didn't account for. So here you can see, for example, Forest Glen, one of our patches, had this small creek running through it and this adjacent like grassy trail, and that was cutting right through the center of the patch, and we didn't consider either of these features as an edge, even though they might have a similar behavior and a similar effect on the tree canopy and on solar radiation. Um, so we think that future work should probably account for these interior edges in forest patch analysis. We also treated all patch edges the same. So basically we said like when the forest patch ends, that's the edge, and like we left it at that. Um, but in reality, there were a variety of edge types. So here you can see one of our patches was right next to this uh, very large highway. Some were bound by rivers or streams. Some had these like fields next to them, or some were bound by paved trails. And we think that these different urban characteristics could very well influence the tree canopy and the forest structure and below canopy solar radiation. So we'd recommend that future work delve more into edge classification and look at the influence that these different urban environments might have on solar radiation inputs. And finally, returning back to this original schematic to describe our project where we looked at the influence of patch attributes and below canopy radiation on these understory processes, these different ecological processes. We've now looked at the top of this chain, and we'd encourage others to look more at the bottom part and kind of study the relationship between solar radiation and these different functions and processes to see to what extent do the variables we looked at really influence the ability of urban forests to provide ecosystem services. And with that, I'd like to thank you all again for being here and to thank my committee members, Dr. Pavel Zuckerman, Dr. Baker at UMBC, and Dr. Tilley. I'd also like to thank everyone in our lab group, as well as the folks at Dr. Baker's lab who provided a lot of the data for this study. And finally, I'd like to thank my dad who joined me all summer doing field work and made it possible for me to complete this project during the pandemic. So thanks again, and I'd be happy to take any questions.
Very cool. Well, that was a really interesting talk and evidenced by the fact that there's lots of questions for you. So I'll let you take a breath here. And then the first question was from Adele, who compliments you on great work and is wondering about getting rid of overexposure by adjusting your photos. Can this cause an error in computing your diffuse radiation?
So capturing the photographs, we're basically just trying to get this clear delineation between the tree canopy and the sky. For both radiation values, like that's kind of making sure it's not overexposed or underexposed is really like essential. So if we did have like spots that were like darker than they should be in the image, it would have affected the computation of both diffuse and direct radiation. But if our image was just like had a clear element of sky and a clear element of tree, the getting rid of overexposure shouldn't influence any computation of either radiation value.
Gotcha.
So we're not measuring radiation in the field.
Right. Okay. Another question related to radiation, and a question I actually also had and Dr. Weil had, did you test whether the aspect affected the direct radiation as opposed to the diffuse radiation?
So we did not, and that would be something probably that would be good to do because we would expect that direct radiation would respond much more strongly to the aspect and slope than diffuse would. We were looking just at total radiation. The image I showed, let me see if I can pull it up. Sorry, 1 minute. So here, this is actually a measure of just direct radiation, and they didn't really see much of a change in summer. So I don't think that in the end it would have really impacted our kind of findings, that slope and aspect didn't have much of an influence on solar radiation, but that would be something good to look at too.
Could the near edge images capture sky at the forest edges, and would that have been included as non-canopy?
Yes, they would. We did our best to kind of only pick sites that were far enough into the forest canopy that we wouldn't have like large portions of like just open sky just because we were outside the canopy. So we tried to get all of our pictures at least like 5 to 10 meters into the forest patch.
Let's see here. Did they account for the intensity? Did you account for the intensity of the solar radiation? Usually maximum solar radiation is received when the sun is at its zenith, usually around 1 and closest to the earth. It seems there's measurements with the camera images related more to leaf area index.
Yeah, so through those images, we're able to model solar radiation. So we're modeling it across time. So from those same images, you are able to assess leaf area index and a couple other canopy characteristics. But we were just looking at solar radiation and we modeled it across throughout the full summer months. So basically you like input these solar radiation values into the software and then use that to compute solar radiation over time. And the values that we input were from BWI. So like NOAA collects those solar radiation values. So we took those values from the summer months, an average of the summer month inputs, and then just modeled it with the tree canopy cover.
Okay. Actually, to follow up on that, did you make any actual radiation measurements to validate that?
We did not. That wasn't part of this project.
Let's see, let's go on. How about were the forest stand delineations conducted by the LTER to determine the age and structure between these site comparisons?
So the LTER and UMBC and the people at the Forest Service did look at a number of different characteristics. I know I have like stand density and that kind of stuff. I don't know kind of to what extent they looked at the different ages or composition. I assume that data is somewhere, but I don't have it with me.
Yeah,
That wasn't part of it.
they have it. It's not as precise as the things that are measured directly on site, but some of the Forest Service people do have that information.
Oh, okay.
Yeah.
Let's see. And this is the question I also had, and Deep had, and it's, why did vine invasion increase soil radiation? So would different
Yeah,
vines and native vines be different in that effect?
yeah, I had it kind of at the beginning when we were thinking about how vine invasion would impact soil radiation. I saw like kind of multiple theories that it might increase it or decrease it. And what I observed on site was that typically the trees that were heavily invaded had like absolutely no canopy cover. Like the vines were all like attached to the trunk and to the branches, and there was just no canopy left. So we think the vines, or like most of it seemed to be English ivy. So we think that just kind of killed off the canopy. So that's why we would see that relationship.
Okay, so then, yeah, so native or invasive vines would make a big difference. Although I guess in this case, these are all kind of invasive in these areas, right?
Yes, I think so.
Okay. And let's see, by the way, I did save the chat and I will text it to you, or I email it to you so that you have it. I'm trying to make sure I hit all the questions here. Let's see. Oh, did you express radiation as joules per area of land or plane area, which would affect the slope of influence, the scope of influence?
It was in joules per square meter. And basically like the images themselves don't they don't capture area. Like you can't tell the area from the image. You just kind of can understand angles. So that's kind of why that unit was used.
Very good. Well, that's awesome. Well, again, thank you so much for a really interesting presentation. I'll remind everybody that's on to please go and follow the link that Marty just posted at the end of the chat, and evaluate Ruth, so give her some feedback on the presentation. As I mentioned, I'll send the chat to Ruth and Mitch so they have it, and otherwise I think we'll be good for today. So thanks again.
Great, thank you.
Great job.